So first off, thanks for coming. Thanks for enjoying a little bit of our hospitality with beer, pizza. We're very proud to celebrate the launch of 1.0. It's a good crowd. I want to thank our speakers in advance. I'll thank them again beforehand, but I know some people travel from far and wide, so it's a pretty big deal for us. So Duffy and Mike are going to talk about some Kubernetes apps. Christian came up from California this morning, and then Rimma and Mikhail. I think Mikhail wins the award for traveling furthest away. Sorry. Oh, okay, great. How long was your flight?
10 hours.
10 hours. So I think that's quite Pulumi loyalty. So how many people are from Seattle? Not bad. How many people are not from Seattle but still from the US? And how many people are not from the US? Oh, it's pretty good. Not bad. So thanks for joining us. How many people have actually written and deployed resources using Pulumi? Not bad. How many people have tried Pulumi but not actually all the way to production? Okay, and how many people have never tried Pulumi? Good. Okay, so we'll have a good mix, good education overall. I think we were trying to decide whether to kick off with a little bit of a quick demo before we get to Duffy and Mike's session. So with that, I'll hand it over to Joe. Joe's literally going to show Pulumi in 5 minutes, a quick tour around the block. And then we'll get to the regular talk. So thanks for joining us. I hope you have a great time. We'll have a bunch of time at the end for questions and socializing and all that other good stuff. So without further ado.
Cool. Thanks, Eric. And thanks for coming by. Definitely appreciate everybody coming out. And 1.0 has been a huge rally cry for the whole team. It's really helped us focus on end user, kind of basically making it easier to use. I think the key feedback we've heard from a lot of people that have tried to get up and running with Pulumi is like they love the idea, and it turns out cloud infrastructure is kind of hard. So we've been really working hard over the last couple months to make it as easy as possible. So because not everybody knows what Pulumi is, I'm just going to do a quick 5-minute kind of overview of why Pulumi is a little bit different than the typical take on infrastructure as code. And then I'm going to turn it over to Duffy and Mike to show you secure production-ready Kubernetes apps. So the key thing with Pulumi, and Eric and I, our backgrounds were from developer tools. We were at Microsoft. We worked on kind of platforms like .NET, languages like C# for longer than I care to admit. But I kind of, when we came to the space, we're super excited about just infrastructure in general, the rapid pace of innovation in cloud platforms, containers, Kubernetes, serverless. But when we started getting our hands dirty, it was like learn another YAML dialect that has Go templates embedded in it, or a DSL that like maybe for loops were coming, but they weren't quite real for loops, and there wasn't really any sharing and reuse. And so our approach was, hey, what if we just took general purpose languages and married that with everything we know about infrastructure as code, right? Which is, infrastructure as code is great because you sort of contain the complexity of your infrastructure by getting previews of things before you deploy them. You can get diffs. It's not like open coding against cloud SDKs or writing Bodo scripts. It really is a much more robust way to do deployments, to manage infrastructure. And so what we said is, hey, what if you could take everything we love about languages, sharing and reuse, you can use IDEs, you can use test frameworks, but we wanted to take that and actually retain everything about infrastructure as code. So that's kind of what Pulumi is. So the idea is right now, so it's a multi-language runtime. It's open source. It supports TypeScript, JavaScript, Python, and Go right now. So you basically just author your infrastructure, and it is declarative. This is one of the common misconceptions because it's a general purpose language. People assume that it's going out and mutating infrastructure as you run it. No, it's actually building up a declarative model of your desired goal state. Much like a CloudFormation, an ARM template, or a Terraform HCL file. It's just that you're doing it in language. So you get functions, you get classes, things like that. You can deploy with our CLI, so we've really made it as pleasurable to use for a CLI as possible. Some people said, oh, I didn't know a CLI could do those sorts of things. It's got nice little animations. And used to have emojis, but the team deleted them because they didn't like them as much as I did. But But we've also worked a lot on integrating into CI/CD environments, especially as we go into production with a lot of customers. They're using GitLab, they're using Spinnaker, Octopus, like all of the CD systems. So it's important to us that we weren't trying to replace them, we were trying to actually integrate with them. And then we've got a console. And so we sort of built it a little bit differently than existing tools. We built it as a free state backend by default, and then if you want to manage state by hand, you can do that. But we've got a sort of nice web app that makes it really easy to keep track of state, so that if you're in a team environment, you don't have to worry about, hey, is the state properly locked and backed up? So this is just an example that, once you have languages, you get abstractions, right? And so this example is 27 lines of code. Sorry, the resolution isn't quite what I imagined, but you create an ECS cluster, associate a load balancer with it, allocate a private container registry, an ECR, and an AWS, build and deploy a Docker container to it, and spin up a load balance service, and then export the resulting URL, all in 27 lines of TypeScript. You run Pulumi up, and it just provisions all this stuff. We understand the language, so we know all the dependencies, so we can parallelize deployments, we can do the teardown, in the right order. And so this just shows you the power of abstraction. And of course, we support AWS, Azure, Google Cloud, Kubernetes. You can even mix and match. That's one thing that makes Pulumi a little unique. The EKS cluster I think might refer to, but spinning up an EKS cluster on Amazon is actually not very easy. It turns out, there's EKS Cuddle, which is a special purpose tool. It turns out the challenge is you need to orchestrate deployments between AWS resources and Kubernetes resources, and CloudFormation can't do that. And Terraform, doesn't really have full support for the Kubernetes object model. So the magic we've been able to do is mixing these in the same sort of tool with the same workflow, which is pretty powerful. I mentioned integrations. I think one of the key things with 1.0 is, what does 1.0 mean to us? Well, it means it's complete. So we've worked with enough customers where we've actually brought it into production. Lots of startup customers, but also larger Global 2000 enterprises. And along the way, we've had to add a lot of integration points around identity providers like SAML SSO and Active Directory, and also CI/CD systems. I mentioned the pluggable state storage, so a lot, because the default experience, which frankly we're trying to make a little clearer for our end users, the default experience is to use our SaaS for state management, but it turns out you can actually, just like with Terraform, for example, you can manage it in your own S3 bucket. If you don't want to share the state, with our service, you can do that. A similar thing with our secrets management system, so you can easily do encrypted deployment time secrets for tokens and passwords and things like that. We actually encrypt it in the resulting state. And in fact, we transitively encrypt anywhere that secret goes, so you don't have to worry about it leaking. But if you want to use HashiCorp Vault or KMS or anything, we actually have integration points for all of these things as well. And then, I encourage you, if you're kind of coming to the system, you're like, hey, I don't find much value in the SaaS, I'd encourage you to take a look at some of the features. It's actually quite handy around things like webhooks. You see a lot of people building Slack bots and custom integrations and things like that. We also have, this is a recent addition, also the ability to import state from existing clouds, which most people coming to Pulumi are not coming from scratch. They have mountains of Terraform or mountains of CloudFormation, and so we're trying to make that really easy to convert over. So we have a number of kind of options there. And then finally, the major area of focus, frankly, for 1.0, we had a really good reliability, robustness, but documentation, I mentioned at the start, getting started was kind of tricky. So we've now got over 100 tutorials, got a lot of user guides, we revamped all of the docs. So if you looked at the docs 3 months ago and you're like, wow, this is just too hard to use, I'd encourage you to take a second look. It's come a long way. And then finally, I really want to thank the community, because honestly, the reception has been kind of overwhelming. I thought there was a good chance when we launched the open source project that people would hate it. That why would you use a language, like a general purpose language for infrastructure as code? But it turns out the reception was overwhelmingly positive. I think it really came in at a time where people are getting sick of YAML and recognizing the limitations of a lot of the tools that we've been using. I would say the other thing is a lot of people we work with nowadays are trying to help their developers to work better with their ops team. And we really see that by using a general purpose language, at least we're all on the same playing field. Sure, there's still going to be specialization. The DevOps team is really going to be experts in networking and clustering and security and IAM. The development team is probably going to focus more on application level concepts like load balancing and services. But giving people the tools where they can make that a policy decision, so that it's not this like hard wall between the two groups. We can actually sort of collaborate and maybe even share components with each other. That's been amazing to see in the customers that have picked up Pulumi, and I think that has been, frankly, more than the technology, that sort of cultural transformation, if you will, has been sort of the most powerful thing that we've seen with our customers. We are hiring pretty much across the board, so we're scaling up in all areas. So if you're interested, come talk with me, talk with Eric, shoot us an email. We'd love to talk with you, spread the word. With that, I'll turn it over to Mike and Duffy.
For those of you who may not know us, so I am an engineer at Pulumi. I work on Kubernetes focus portions of our product, and likewise Duffy does the same at VMware. And we shared a former life with some coworkers of ours here. Shout out to CoreOS. And in that time, we've seen so many good and bad things about taking Kubernetes to production. More bad than good, and we're here to tell you why we think things are starting to take a different turn for the better. So I'll turn it over to Duffy.
How's everybody doing? So, I'm Duffy, I'm Maui Lion on Twitter. Feel free to follow me. I'm trying to introduce my account, so feel free to follow. I'm talking about Kubernetes pretty much all the time. In this talk, we're actually going to talk about some of the security surface of applications and how to think about them. We're going to show you some kind of cool command line tools, or some tricks about things. I'm also going to give you a quick high-level overview of Kubernetes, and we're going to talk a little bit about what is a container. We're going to talk about, I'm going to give you a quick 5-minute overview of what is Kubernetes, and we're going to talk a little bit about what is a container, and then we're going to talk about how you can use container orchestration, basically the form of container orchestration that Kubernetes takes, to do some things maybe that you don't, as a cluster operator, want people to do. And so we'll kind of go through those examples, and then we'll also show you how you can actually mitigate that. And so this ties into the application security story by actually showing you some of the controls that you have within Kubernetes cluster to actually mitigate some of the risks that are just inherent in Kubernetes. So this first slide just talks about all of the. I'm right in front of the speaker. So this first slide talks about basically all of the moving pieces of Kubernetes, and we're just going to talk about it as an application here. So in this slide. So I'm actually going to step on the other side of it. Go for it. So in this slide we have all of the moving parts of a Kubernetes cluster. So when you spin up a cluster in EKS or in some of these other environments, you really don't have any idea what's happening inside of the dotted box. It's kind of happening outside of your control. But if you're actually standing up a Kubernetes cluster in other environments, leveraging some of the open source projects like Cluster API or KubeADM, then you actually get to see all of these pieces working together. Let's talk about what they are just really quickly, give you a high-level overview. The API server, as you can tell by all of the arrows, is basically kind of like the center of the universe within Kubernetes. This API server does exactly what you might think it might do, right? It's going to do things like validate resources that are being submitted via the API. It's going to handle things like authorization, authentication, those sorts of things. It's actually also where admission control happens, and we'll talk a little bit about that as we move down through the talk. Below the API server, we have the controller manager. This guy's job is actually to have a number of control loops that basically iterate over and over again and try to break down a higher level of abstractions, things in Kubernetes like called deployments or stateful sets down into pods or the lower level of abstractions. Then we have the scheduler, which does what the scheduling things, right? It associates work with actual nodes. And as we're talking about nodes, we can look over here on the right, see 2 kubelets and a container runtime. This is actually where all of the heavy lifting happens. When we were talking about pods, that's actually the schedule, the minimal viable schedulable resource within Kubernetes. Those pods are actually realized on the kubelet, and the kubelet takes care of the life cycle of that real process running on a server somewhere. That's what the kubelet's job is. Lastly, we have etcd, which is basically a key value store that stores the state for all of the Kubernetes clusters, or all of the state within Kubernetes. That's a quick overview of all of the components. Let's talk about a flow here. So in the previous diagram we said kubectl apply pod. We're going to actually be doing that live in a demo. I want to talk about what actually happens under the covers when these things happen. The reason I think this is important is because Kubernetes itself is a distributed system and a loosely coupled one at that. Once a pod is actually created, that pod object or spec is being submitted to the API server. API server goes through the process that we talked about before. Once it's actually allowed admission into the cluster, that pod spec is persisted into etcd, the key value store, and then the API server returns 200 OK. You've given me a resource, I've accepted it, we're done. The next thing that happens is that the scheduler, upon determining that a pod has been created but is not associated with a node, will actually take that pod object, determine where to schedule that object, and then persist back to etcd the node name field, or the selection that it makes. And again, the scheduler is now done. Doesn't do any more work than that. It basically just populates that node name field based on the predicates that are provided by that pod spec. The next thing that happens is actually the heavy lifting. We're going to start this process on a kubelet somewhere. So kubelet will actually also have a watch on the API server. It will see that there's a new pod that's been defined. It's been associated with this node. I'm going to download that spec and start doing real work. I'm going to start those processes that are defined within those containers and run them on a server, and manage the lifecycle of them. And I'm going to report back up to the API server things like status. One thing that's interesting about this slide is if we go back to the previous one, we can see that there's a controller manager in this diagram, but there's not a controller manager in this diagram. This is a loosely coupled system. I've defined a pod, which is already the lowest level abstraction. This is already the lowest level primitive, so there's nothing to break down into smaller primitives. There's no need for a controller manager. If I had specified within the pod spec a node name, if I had populated that field, I could take the scheduler out of this picture as well, because there'd be no scheduling to do. And we're going to show what this means and why this might be like a security service for Kubernetes clusters in general. That was my 5-minute Kubernetes talk. That was a little more than that, but it's what it is. So next I want to talk about what is a container. How many people, actually in the room, I should have asked this already, but how many people in the room are already pretty familiar with Kubernetes? Right on. Well, the rest of you did that kind of a crash course override of what it is. How many people in the room are familiar with containers? How many of those people can tell me what a container is in reference to a Linux kernel or a process? We're about to expand your horizons. When you log into any Linux host and you type ls-al/pid or /proc, the proc file system, and then some pid, and then the directory ns, you will actually see a mapping that represents what a container is. In general, all of those things within that mapping, and we'll show this when we do the demo part, will agree on the particular namespaces that they're associated with it. But effectively, every process within the Linux kernel has the primitives necessary to define isolation on a process level. Right? All containerization is basically just making use of all of those primitives to provide a different mount file system, or a different container file system that's shipped with your container, or a different network namespace associated with just that one pod, or a different PID namespace, so that when you're inside the container, the only process IDs you see are the ones that are associated with that particular process. Right? This is just process isolation. And this is the kind of the aha moment when we think about what the difference between virtualization and containerization is. Right? Containerization is process isolation. If you start a process within a container and that process dies, the container dies. If you start a process within a VM and that process dies, the VM doesn't care. It's going to keep going in perpetuity. This is the key difference between the two when you think about it. We're also going to talk a little bit about Docker and Docker. How many people here know what Docker and Docker is? A few more of them than I expected. How many of you think that Docker and Docker is exposing the underlying Docker socket on a container host to the container? One. How many think it's actually exposing enough privilege to the container to create container primitives directly? Nobody here. All right, we're moving on. All right, I get it. Okay. So this is actually a description of what a container is when we think about like all of the different namespaces. We talked about what they mean. A container is a mount file system. This represents the actual Docker image, that file system that ships as part of your Docker image. A container file system, any shared mounts, like if you actually have like persistent volumes or anything else like that, those sorts of things are actually associated with a particular container. All of these things are Linux kernel primitives that are together represent what a running container might be. And you can do things like limit things like memory, CPU, I/O. You can do things like create different network namespaces. You can share all of these things between containers within a particular pod inside of Kubernetes. And then there's also a set of constraints that you can apply. Like you can define Linux kernel capabilities, like whether you want to be able to provide through the container the ability to manipulate the network of that container. There's quite a lot of constraints that we can define. And we're going to talk about like what that surface looks like within Kubernetes as well. So that was the quick crash course of Kubernetes and containers. Now I'm going to show you some kind of like maybe not so great things. I'm creeping in front of the stand, like right in front of the speaker, so that I don't feel it. All right.
You are literally
You are, yeah. Or EM shield. Yeah. So this is a one-liner that actually allows any authenticated user, in the absence of admission control, to take control of the underlying node. And this is leveraging the kubectl command line tool that ships with Kubernetes, and what it does, effectively, is it will actually just deploy an Alpine Linux image, and it will use nsenter to mount the underlying node's PID namespace and file system, and then we'll actually use nsenter inside of this container to basically take over the underlying node. This is possible for any authenticated user inside of a Kubernetes cluster within the absence of admission control. So let's show that off a little bit. What I'm going to do is I'm going to show you the actual manifest I'm going to use this, and basically it's just like that one-liner, but I've actually just created a container that will actually allow me to schedule this directly on a host. And just like we were talking about before, with the direct scheduling attack, if I populate the node name, I don't have to have a scheduler running. I can actually pick any node that's registered with the cluster to target with this particular attack. So I'm going to go ahead and apply that manifest. And I'm going to exec into that container and look at the result of nsenter. Nsenter is a tool that can be used to enter into any of the namespaces associated with any given container. It's a great tool that really exposes a lot of capability for interacting with all of those primitives that make up an actual container. I've used nsenter to solve the mystery of like how a pod is actually configured. Like if I wanted to understand what ports are actually going to be bound to a specific pod, I might want to actually see like, you know, the result of like ss-ln within a container and see like what actual process is actually bound. So in this case, what I'm going to do is jump into an NSX pod or an Nginx pod, and I'm going to look at what ports is bound into. And so in this case, the nsenter command basically allows me to enter the network namespace of that running container inside of my local machine here. Basically only by identifying the process ID or PID ID that is working on this particular node. Once I enter in, I can do things like ss-ln, which is kind of like the equivalent of netstat-rn, and I can see that this particular container is binding on port 80. So that explains my mystery, right? It wasn't working because it wasn't designed to work the way I expected. I can also mount it to the file system and look at the configuration of these things. Now what's interesting about this is that I can do these particular things even if the container itself doesn't have a bash or doesn't have a shell located. Talk about what this is. So this is actually that mapping that we were talking about before. And so in this particular container, we can see the mapping between the C group, the IPC namespace, mount, network, PID, all of those things, and a particular number. These numbers are specific only to this pod, or this container. If you SSH into a host and you looked at all of the rest of the processes, you might see that they all agree on this thing. But what else can we do here? As we talked about Linux's namespacing all of the things all the time, we can also use NSFW to take over the host without host path. We haven't talked about host path, but we did get possible. So in this command, I'm actually going to use NSFW again. I'm going to enter all of the namespaces associated with pig 1. Now what's neat about this is that basically what this allows me to do is get root on the underlying host. This one liner allows me to actually completely take over the underlying host. Right? I can do IP adder. I can see the underlying host. I can do pretty much anything inside of the space. I have complete ownership over the underlying host. And this is possible in any Kubernetes cluster in the absence of permission control. So that's what an authenticated user can do inside of Kubernetes. In the absence of permission control, they can do pretty much anything to the underlying. How do we fix it? How do we actually stop that from happening? The only surface that we have to actually control this is admission control. And this gives us the ability to validate or mutate resources as they're defined inside of the API server. So in this case, I'm actually going to show off pod security policies and how those things can actually allow us to limit the scope of this particular type of attack. Pod security policies act as an admission control for your Kubernetes clusters, and they allow you to limit things, constrain things in a reasonable way. Pod security policies give you the ability to define things like within the particular pod spec, within that container that we created. You'll notice that I set the privilege flag. Well, I can set a pod security policy globally within the cluster that says nobody can define privilege flags. And if I needed more than that, then I can actually allow only those pods within a particular namespace to have that capability, but deny everybody else that particular capability. Same thing with the underlying host file system or host network or capabilities, all of those things. I can constrain all of those with pod security policies and apply them cluster-wide. Now the ordering of pod security policies is a little tough to wrap your brain around, and the UX I think could use improvement. But generally what happens is that the ordering of pod security policy application will be validating before mutating, which means that if you have defined multiple pod security policies within the scope of a cluster, whatever entity it is that's creating that pod, if they have access to multiple pod security policies, the first one that actually allows admittance without mutating the object will win, and only that pod security policy will apply. They're not additive, they don't accumulate or aggregate. It's just the first policy that applies that doesn't change the object will win. And if no validating policy applies, then it will go through the mutating ones. And again, even a mutating one, only the first mutating policy will actually affect the pod, because at that point it has been accepted. Pod security policies are tough to work with because they actually tie into RBAC. We have to think about the entity that would be creating the pod and associate pod security policies with that entity. Within Kubernetes, we talked about the controller manager. The controller manager is responsible for running things like the deployment controller, replica set controller, and those sorts of things. Those entities are responsible sometimes for creating pods directly. And we have to associate the permissions to those pod security policies that we want to apply to them, to those specific controllers, or to groups of users. So let's do all of this with Pulumi.
Thank you, Duffy. So as Duffy pretty much showcased, this is pretty ripe for picking, right? If you're looking to attack a Kubernetes cluster without having default PSPs in place, pod security policies, you're pretty much out of luck. So the beauty of that is that in every single provider, what essentially happens, whether I'm running on Azure, whether I'm running on EKS, or if I'm running on GKE, they all come baked in with their own pod security policies, and most of them are pretty wide open. So they allow a blanket kind of policy that anything goes. That is not something you want to roll with out of the gates. So the good thing about managed clusters like EKS and GKE and AKS is that they give you a cluster, but that is a vanilla cluster. You cannot actually use that, right? Not in production. So the cool thing about Pulumi is because we support many SDKs across all of our platforms, I've literally defined 3 clusters in 3 lines. That is pretty powerful. If I want to actually go into the actual clouds, I can go and inspect that based on our SDKs, like on the column on the right, here's my EKS cluster. I define my VPC that it's going to be deployed into. I deploy some roles. I set the properties of the cluster itself, the version of Kubernetes, and then I map in some roles if I want to actually take over as a different user. When I deploy this, what actually is given to me is 3 different kube configs. One for EKS, one for AKS, and one for GKE. I also deployed a kind cluster. It's a Kubernetes and Docker cluster, and that is just local. So essentially, all you need to work with the Kubernetes cluster in Pulumi is a kube config file. We wrap a provider around that, and in Pulumi, that is the object that you work with. So this is pretty neat. I don't want to bore you with the details of setting a cluster up, but this runs and you get a couple of clusters. If I switch terminals here, I'm now going to deploy something into that. So because we have all these SDKs available, and because each kube config is wrapped up in what we call a provider, you can now simply put this in a for loop. Hey, look, we actually have a real for loop. And in that for loop, we can do a couple of things. We can define our own default pod security policies out of the gates that replaces all of the blanket allow that all these providers put in, and then replace that with something more coherent that actually makes sense. Not to mention deploy a real application into that. So this just kind of shows off how I can deploy Nginx with this load balancer into all of these different clusters. And so if I run an update, which I've already done for all of us, I get all this output, and I can literally go to Nginx on Azure, I can go to Nginx on EKS, I can go to Nginx on GKE, I can go to Nginx on my kind cluster. But wait, I'm getting yelled at because I don't have the authority here as an anonymous user to do this. Why? Because my default pod security policies have revoked all of those open wide privileges. So the neat thing about that is that we can not only set our own defaults, we can now showcase that we've provisioned all of our infrastructure, IAM, all the networking, the cluster itself, and then once the cluster is up, we can hook into that cluster and deploy anything else that we needed to have. So in this case, we have pod security policies. Pulumi, by default, our SDKs do not manage pod security policies, but we have this notion of what's called a dynamic provider, something that I can create a CRUD interface on, and I can manipulate to my heart's content. So in this, I've gone in and I've said, look, for each of these providers, some of them come with defaults that I cannot strip away. GKE, for example, if I were to remove all these pod security policies from GKE, all of their stuff would break. Likewise, in a very kind of wonky manner, AKS comes with its own pod security policy, but if you try to delete this root privileged pod security policy, they have an add-on manager that will add it right back in seconds later. So what do? We have to at least scope it to our capabilities to make sure we have least privilege, and that we have some control of what comes in after the fact. Because again, the Lego blocks that we were given as the provider, they stop once that cluster is up. So it's on us to take the ball from there. So I decided to say, these are the required cloud security policies. And if you've worked with Kubernetes, I decided I'm going to create my own pod security policy. I'm going to create my own demo privileged pod security policy and my own restricted policy. But they're each going to be gated to different groups within Kubernetes. In this case, only the service accounts in the kube system namespace. So what does that look like? So if I go ahead and go into Pulumi, one of the neat things is the code is the state. So just like I deployed the Nginx app, if I were to comment that out here, that code is no longer live. And, take that on here. And if I were to rerun an update, what will happen is that because I removed the code, that deployment will go away. So you have a much easier way to work with the infrastructure, with the state that belongs to it, and this feels more intuitive to what we all want to work with.
You can iterate over these things, practically, right? You're not in a situation where you have to define it all up front. You can just continue to iterate until you get it right.
Right, and so the cool thing is, you can do that on so if you're testing, let's say you want to do a testing across all these Kubernetes clusters, you can visualize what that would be like. And again, the code is the desired state. So that's going to go off and delete, and all the deployments are gone. Now, to talk to what Duffy was really getting to is, by default, we don't have the greatest pod security policies, so we bake in our own. I created this cluster as the Pulumi user in AWS, and by default, whoever provisions the cluster gets super root on all of this. So the super root can do whatever they want. Now, to show that, because the provider is just a kubeconfig file, I'm going to show what it takes to deploy a root privilege pod and the Docker and Docker pod that Duffy was talking to here, and show that the super root user can in fact deploy this as we expect. So that'll go off and deploy in about 15-20 seconds. And as we expect, because I am the super root user, all of these pods will come up. And again, I'm leveraging my kubeconfig file that I created as super root. And that's just defined as the provider. And it's just a property and how you deploy the actual pods, or the deployments for that matter. So as you see, the pod comes up as we expect. I am super root. Let's go ahead and blow that away and try that as a different user who's scoped to a more finer-grained RBAC and who's not allowed to do this because they're forced to a restricted pod security policy. So I'm just going to blow that away real quick just to kind of show you a clean slate. Give that a couple seconds. But the cool thing about that is, because we can just mix and match all of this, because in Kubernetes everything is a kubeconfig file, that gives you so much flexibility about how you manipulate, how you manage, and how you actually work with the clusters. And again, because we can hook into the cluster after it's up, that gives us the ability to actually set our standards, to set all our best practices, to limit actual capabilities, or even set proper defaults that we may need. So that'll go off and delete the pods from the super root user, and that'll be done in just a second. And I'm going to go ahead and set this up for the next user who's finally scoped. So I created an additional user called BetterMike, because BetterMike knows better than to run in a privileged setting. And BetterMike is actually scoped with IAM and EKS to be only using this finer scoped rules here. They can only create pods deployments, replica sets, and PVCs within the default namespace. Anything else beyond that, they're going to get yelled at. So if I go ahead and save this, and I run it as my BetterMike provider, which is my kubeconfig file that the BetterMike has, I will get Pulumi to show me a little bit more different output this time around. That shows that we can not only bake in our proper defaults, and then on top of that, leverage RBAC to tell us that we are not allowed to be doing these things. So I'll give it about 10 more seconds. And shortly enough, we should get a warning. There we go. And it says, sorry, we cannot run these containers because the BetterMike user is not allowed to run a privileged container. They're not allowed to use the host file system. And that by itself is miles ahead of what we would ever have the capability of doing with any other tool. So with that, let me switch back to the slides. So that pretty much does it on our end. If you have any more questions, there's our QR code. Just point your camera at it. It'll show you the link to all of our slides, to all of the repos, and look for us after if you have any questions. Thanks.
Both companies are collaborating, so if you're interested in working in this space, you can meet anybody at this table right over here, or Mike or Joe here at the top. Thank you very much.
So next up we have Christian. Christian works at Solvvy, and Solvvy was one of our earliest customers. And Christian's going to sort of give the do's and don'ts of working with Pulumi, so sort of best practices overall, and some of the battle-scarred, hard-fought, hard-won lessons that he's learned over the past couple of years. Actually, it's been a long time.
All right, everybody. So, welcome over. I'm actually, my name is Theilemann. I'm a senior software engineer at Solvvy, and which is like a 50-person startup. And as Eric was already saying, we're one of the relatively early customers of Pulumi. We started using it in August last year, and we use it for almost everything on our infrastructure in production since about January. And I just want to talk a little bit how we use it, why we use it, and what are some of the best practices we learned over time. So about me, I'm a senior software engineer. I focus mostly on infrastructure and platforms. I make most of our tooling decisions, provision the infrastructure, and make the rest of our engineers a bit more efficient. But by background, I'm actually like a full stack engineer. I work a lot on web apps and stuff like that, and I just happen to work a lot on the infrastructure in the last year. So. Quickly about Solvvy, so we are a 50-person startup. We do a bunch of machine learning to automate it only on customer service. Some of our customers are, for example, Ring. So for example, when you go to the website of Ring and you ask a question here, it's actually going to our UI and our backend, which is a bunch of machine learning, and across a bunch of websites to build a knowledge model which may or may not answer some of those questions automatically. Our stack is primarily Kubernetes on GCP, and then the backend we use for the most part Python and Node.js. And as I mentioned already, we use Pulumi for managing the infrastructure, but also the application. So that's kind of important. We don't like just set up VPCs and clusters, but we also deploy into our cluster using Pulumi. If you're interested about our stack in detail, you can actually go to this website. How and why do we use Pulumi over anything else? So in 2018, we started a project to modernize our entire infrastructure because we had a lot of problems with cost, stability, and velocity of deployment. And this was not just because there was a lot of things wrong. And we were using before that raw EC2 VMs, which are for the most part managed by Ansible, lots of custom bash scripts, a bit of Jenkins, and some steps which were documented or not, or in somebody's brain. A key decision at that time it was beginning in 2018, so Kubernetes was already fairly popular at the time, so we wanted to do something which looked very promising, and that was Kubernetes. And to run Kubernetes, we decided to use GKE on GCP because it takes away a lot of the burden of managing the cluster itself. And we started setting up a bunch of GCP projects and Kubernetes GKE clusters just using Terraform, and it was kind of working fine for the basic things. However, where the things were a little bit more ambiguous and not clear what to do was for deploying Kubernetes applications into your cluster. And we started just using raw or SMB templates and YAML files. We looked at Helm. Who in the audience actually has used Helm before? And who of you actually likes it? Yeah, so that's kind of the feeling we had. So Helm, it introduced a lot more complexity than problems it solves, in my opinion. We looked at Casey, which is conceptually great, but it is a kind of awkward language. We looked at Audacity, Reflux, even tried out Terraform, and later about Terraform, I think it's not that great for deploying into Kubernetes. And then we used actually for a couple of months Forge, which is like similar to Scaffold. It builds your containers, templates a bunch of YAML, and deploys into your cluster, but it's super opinionated, and it cannot be really extended for more some advanced use cases. So in August, I found Pulumi, I tried it out, and I was from the get-go really impressed, really on how good it was working for a product that literally just came out of private alpha 2 months ago, such a young team, and it was honestly at a time already working better than a lot of the tools which have been out there for 1.5 years or so. And it gave a lot of confidence into the team and the company that this is like a good platform and better. And concretely, I think some of the two key advantages that I personally see with Pulumi is over most alternative tools is that it has really the best-in-class Kubernetes support. And one reason for that is, like, when you look at the team, they have a bunch of folks which have been working for Kubernetes for a couple of years. They have folks who have worked a lot on language technologies. And what they do is actually they auto-generate a large part of the Kubernetes SDK by introspecting the open API spec from the Kubernetes. And that's when Kubernetes 1.16 comes out and introduces a new feature in Kubernetes. It's very likely that it's very soon in Pulumi, but not in a lot of the other tools. So, I mean, just to give you like an example, I actually put you some links. For example, Terraform, right, also has a Kubernetes provider. However, when you look into just the change, like you can see, well, they added now support for Kubernetes API service, and somewhere down here they added support for deployments and things like that. In 2018, Kubernetes, the Terraform provider didn't support Kubernetes deployments, which is like so essential to anything you do with Kubernetes. So it was not practically usable. They added it in the meantime, but there's always a large delay compared to Pulumi, because Pulumi auto-generates everything. Terraform has to have like hand code support for each resource. And the next, the other benefit is basically, the other big benefit is you can just use your regular program language, which is TypeScript. And you can also use Python, but we use the TypeScript variant of it. And it's so easy, right? We happen to know and use it already before. It's not like we need to learn this DSL my background actually software engineer, and I'm used to use really major high-level languages. And when I started doing all this infrastructure stuff, I was like, why does everybody needs to invent their own DSL for everything? So it's like, it just didn't make any sense. And Pulumi is great, and they just leverage all the existing ecosystem. So they use for package management, they use NPM for editor support. TypeScript and JavaScript is well supported by almost any editor. You get code compilation, static type validation, and you also get to use a lot of reuse libraries. And a lot of those reuse libraries, they're not really written for usage in with Pulumi, but sometimes they come actually really handy. So if you just need to convert, for example, a TOML file into a YAML file, you can actually do it super easy with a JavaScript library, right? And then deploy this YAML file. And sometimes you have use cases where you have an application where you need to inject your TOML file in GitLab runner, for example. And most importantly, you can basically use a single tool and language both for your core infrastructure and the deployment of the applications. And in our case, even the application code itself. So basically we're using one language for oftentimes 3 different things. So with that in mind, just wanted to talk a little bit about some of the best practices that we established in our company over the last couple of months on how you structure your projects and repositories. So typically speaking, what you have is a core infrastructure repository in which you deploy, in which you put your VPCs and clusters, and some stuff like a database. Basically, kind of resources which are shared by a lot of your services, a lot of developers. And I can actually show you real quick how it looks in our case. So this is actually this infrastructure core repository. And we have a bunch of subdirectories here. And for example, we have like a Solvvy dev project here, which underneath contains like a project, which is actually a Pulumi project, which creates the VPCs, configures some DNS stuff, and some IAM roles and things like that. Then another high-level project we have is API cluster dev, which actually sets up a Kubernetes cluster and installs a bunch of like common services into it. One such service is, for example, Cloud DNS Manager, which actually here it's just like a small Redis library or modular written, which deploys Kube external DNS, which is a Kubernetes extension, into the cluster. And it looks very YAML-ish, but it's kind of TypeScript, right? I use actually this thing here, this Cloud DNS Manager class, in all of our clusters, and I just import it here and say, well, use this as the main filter and things like that. And this is going to deploy the cluster so that the cluster actually manages our DNS entries for applications that we have deployed into that cluster. The next thing, and what I wanted to mention is what we should, oops, that was the wrong application. The next thing is you should be aware of this feature called stack reference in Pulumi. So what you can actually do, if you have multiple projects or stacks which just somehow have some dependency in between, you can actually pass using stack reference information from one to another. And commonly you have this, for example, in our case, we have like here one project called Solvvy base environment, which sets up our database. And what I'm here exporting is actually like the IP address of the database and some connection strings for certain schemas in the database. And then in our application repositories, I can just import that connection string in my application. And so that way I don't have to, when somehow something changes, maybe I change the IP of the database server in the future, I don't have to create another commit on top in the other repository. I just redeploy the other repository so that that reads the new value from that stack reference. And I don't have to copy around mention randomly values, so to say. The next thing I want to talk about is like, generally speaking, you should create like your own reuse library for your internal usage, which basically has a few certain best practices and a few things that you often use. So in our case, well, we use GCP and GKE, so a lot of the reuse library stuff is around that. And in fact, I've actually just uploaded kind of a cleaned up version of, I can hide this here. Show an example. So let me just show it to you. So basically we have this reuse library. It's actually really just an NPM package that we have a separate GitHub repository, and this reuse library, for example, has something called Node app. And it has also actually an app. Let's look at this one. So the app one actually is just a Kubernetes Pulumi component resource, which pulls in together a bunch of things. For example, Kubernetes it builds a Docker image, it creates a container, puts that container somewhere down here into deployment, and it also creates like pod disruption budgets if you have like specified some arguments. And also creates a Kubernetes service, depending on if you have set, for example, the Arc service exposed to cluster in general. And like this kind of, because this pattern happens very often when we work with Kubernetes, that you need to build a Docker image, create a deployment, and create a service on top, we have just forwarded that into this app class. And inside our applications, we just import this class and pass a bunch of arguments to it. For the sake of time, I'm going to skip. Like we have some GKE utilities, which are actually pretty handy. But I've actually published the whole library on GitHub, so I'm going to show you the link in the ending. But in general, I would say don't over-engineer this library. Don't don't wrap everything of Kubernetes into some giant class or something like that. We just always every once or 2 weeks we add a new property to this reuse library, which had been used in our case. And oftentimes I'm doing that, but sometimes also other people. And last but not least, you have application repositories. And those are basically your repositories where where's your Python or Node.js or your code that in our case happens to be deployed via Pulumi as well. And in those, we actually use this Pulumi util library. So I can actually show you that really quick. So for example here, I have actually prepared a small demo app. If somebody could hold the microphone real quick or something, so I have actually prepared like a small demo app here. It's just a Node.js application, and I haven't created any information for that application yet. But I'm just going to create really quick the code to deploy this via Pulumi using this reuse library. So the first thing, I have to just create a Pulumi YAML file, which basically defines the Pulumi runtime script I'm using, and the name of it. And now I'm actually creating a subdirectory. So that's kind of a convention. We have create a subdirectory info, which the Pulumi code is, and which the information goes on. Then I'm initializing package JSON, and now I'm actually installing this Pulumi Reus library. We publish this just on NPM. You won't be able to access it. It's a private NPM instance, but as I said, I publish it on Metral. So it installs that, and now in this info subdirectory, I'm just creating a small index file where I say import Solvvy Pulumi util, and I say Solvvy app, and I say new Solvvy app, and it has a lot of parameters, but for the default case, the only thing you need to actually pass is the build context, which is kind of the working directory from which we will build the Docker image. And last but not least, we also need a Docker image. And I could go here and just create a Docker image, but honestly, the Docker image happens to be so similar for a lot of our cases that we put a bunch of Docker files into that npm package itself, and I can actually just reference it by saying dockerfile.node.js, and then it's importing that reference from the utility library and uses that predefined Docker image. And last but not least, the only thing I need to do, I need to say which GCP project I want to deploy it into, and which cluster I want to deploy it into. And that is basically everything I need to do. I think I have done one of them incorrectly. I had created I had imported the Pulumi util writer library in the wrong place. I need to import it in this infrastructure. So last thing I made that basically now the only thing I need to do is I need to run Pulumi up, skip preview, and now it's actually going to deploy. It's built into Docker image, it deploys it into a Kubernetes cluster. It adds a bunch of very useful default configurations, and that's basically about it. You can see the source graph here. That's basically for the demo part, I guess. Last but not least, you should really think about some naming conventions for your projects and stacks. So we, for example, always name our stacks with dash environment name, like dash staging or dash prod. And we use this convention, we introspect in a lot of cases the context on which stack we are in, and depending on that we deal with some if then else branching. So yeah, last but not least, I think when you work with Kubernetes and also still with Pulumi, you still oftentimes have to deal with YAML. And it's actually very useful to know that you can convert YAML very quickly to Pulumi configuration just by converting it to a JavaScript JSON object literal, which you pipe to your TypeScript file, and then you format it. So for example, if I want to use, I don't know, like let's say this example here, just copying some random stuff from the internet, and which you probably often find examples in YAML for Kubernetes. And in order now to just use this in my so basically now so I just use this kind of one-liner here, which uses a bit of Python to convert this into a JavaScript object literal, and so now I basically have here a bunch of JSON, and I can say here group KS4 we want pods, basically this is now already embedded Pulumi configuration. So that's what I do actually work, so this basically stuff I'm doing. Alright, last but not least, I think the last message I have, choose a good CI/CD system. I've tried out about, I don't know, 20 CI/CD systems over the last 1.5 years. They all suck in one way or another, to be honest. The better ones, like some important features for me are to have like manual approvals. So because we deploy everything, we have Pulumi jobs. Sometimes when you want production, you want to have the manual, like you want to have a manual step that you need to manual approve the UI. And last but not least, something called a feature called environment tracking, where the CI/CD system is able to actually track which jobs have deployed to a production or staging environment, and then being able to roll them. And some of the better CI/CD systems I've used in conjunction with Pulumi are GitHub CI, Azure DevOps, and Circle CI. We nowadays actually use Circle CI, which is kind of an exotic one, but it actually works pretty great for us. Check it out if you have some curiosity and are dissatisfied with your current CI system. And I think that is basically the essence of what I wanted to deliver today. Here is the GitHub repository, which contains basically this Pulumi Metral library, which I've shown before. There's a bunch of good goodies there that you can use in your own company, perhaps. All right, thanks.
Okay, so next we have Rimma and Mikhail. Rimma works for Microsoft. Mikhail's kind of doing his own thing. And they're going to talk about global applications, but on Cosmos. So it's kind of, Cosmos seems beyond global, like in the Cosmos. And yet they're going to talk about large applications at scale. So please pay attention, some great stuff in here. Thanks.
So my name is Rimma. I'm an architect and a product manager on Cosmos DB. I'm going to speak for about 15 minutes and just give you a little bit of an idea. What is Cosmos DB? How does it actually work behind the scenes? And then Mikhail is going to show how to build apps, planet scale apps using Cosmos. So roughly, introduction, system model, global distribution. We'll talk a little bit about resource governance. Conclusion. That's my part, and then Mikhail will jump in. So we started Cosmos DB actually about 9 years ago inside Microsoft, and originally it was known as Project Florence. Those of you who have ever been to Florence, there is this famous dome, which is viewed as basically the beginning of the Renaissance. And we wanted to start the Renaissance for data. That's why we named it Florence. We made the service generally available in 2017. It is classified as a Ring 0 or foundational service inside Azure. What that simply means is it's automatically available in all of the Azure regions by default. So whenever we announce a region, whether it's a public, it's a sovereign cloud, it's a government cloud, we have to be automatically there because there are other services that are built on top of us. So we're serving now about tens of trillions of requests per day. Given that we already announced a region in Africa, you can actually take your Cosmos account and span it across all of the 7 continents worldwide. So basically create a database that is spanning across North America, Africa, Asia Pacific, and still view it as a single system image database. Inside Microsoft, it's also became ubiquitous. Services like Office 365, Xbox, Universal Store, Teams, LinkedIn, and now we're also onboarding GitHub and a bunch of other projects. So when we started Cosmos DB, we wanted to build the database designed for the cloud. In a sense, if you were to forget about 40 years of legacy COD, relational databases, how would you design a cloud-native data platform? And ultimately, we wanted to provide capabilities such as global distribution, because cloud is ubiquitous, so your database, your data platform should be ubiquitous wherever your users are. Second is provide the elasticity and unlimited scalability with respect to two dimensions, both storage as well as throughput. So you should be able to elastically go from just a few gigabytes into terabytes and eventually scale into petabytes. And then orthogonal to that, your computational needs may vary over a period of time. So in retail, phenomenon like Black Friday, Cyber Monday, all of a sudden you have a burst in traffic. When you launch a game, you want that game to be successful, so you have a lot of users coming in and you want to elastically scale up. So you want the data platform that can elastically scale with your workload needs. And last but not the least is provide the cost efficiencies with very fine-grained multi-tenancy and resource governance. This is the ability to basically take multiple tenants, densely pack them on the commodity hardware, provide this resource isolation with adaptive resource governance and performance isolation, and provide the guarantees in terms of performance. So these were kind of like the three core principles that we had in mind when we started the service. Now the design goals were, number one is to elastically scale throughput on demand across any number of Azure regions around the world within 5 seconds at the 99th percentile. The other thing is also to provide a near real-time access to your data. So what that means is deliver less than 10 milliseconds end-to-end client-server read and write latencies. On average, it's actually a lot faster. For reads, you will see somewhere between 1 to 3 milliseconds. For writes, it will be somewhere between 4 to 5 milliseconds. Offer 5 nines read and write high availability. Provide tunable consistency models for developers. So this is known as cap theorem trade-offs or pass-up trade-offs, being able to pick precisely the right trade-off in terms of performance, and the trade-off not just with respect to high availability, but also latency and throughput as well. And operate at low cost, that's a no-brainer obviously. And then last but not the least is provide strict performance isolation between both transactional as well as analytical workloads. So something that we will announce very soon, it's already in preview, is being able to run analytics at global scale as well. And last but not least is also build the schema agnostic engine to support basically unbounded schema version. So this is ultimately what it resulted in. So given all of these design goals, at the end of the day, we have a core, the core of the service, which is providing the capabilities like global distribution, elastic scale out, guaranteed low latency anywhere around the world, 5 consistency model, SLAs. We also give you the multiple data models to work with. Because they're built on top of the same core, all of these properties are applicable to graph, to JSON documents, to column family, key value, and whatnot. And ultimately, to access your data, you should be able to pick the API of your choice, because we want to meet developers wherever they're coming from and give you the experience, or your applications the experience as if they're talking to native Mongo or native Cassandra, but ultimately they're taking advantage of the cloud native database. So if you're coming from relational background, we have a SQL API. If you're coming from Mongo background, we give you via protocol compatible Mongo API. If you're using Apache Cassandra, we give you Cassandra API. This one saw the presentation on the NCD. This is the ability to take these capabilities and take them to Kubernetes. So Kubernetes becomes globally distributed with automatic failover, with the multi-master capabilities, and ultimately the SLAs. And this one is the ability to be able to run operational and real-time analytics anywhere around the globe, because Spark is co-located with your globally distributed replicas. So what is the system model? Let me quickly walk through it. This is a beautiful slide, but ultimately the tenants, the customers, they bring their data. The data could be, depending on the data model, could be either tables or collections or graph. We call them Cosmos containers. Disclaimer, it has nothing to do with Kubernetes containers, it has nothing to do with Docker containers. We were not very creative in terms of naming, so we call them Cosmos containers. Ultimately, this is your unit of horizontal scalability. You pick a partition key, and then we perform the sharding in terms of local distribution within the region, and then global distribution across multiple regions. So customers can associate, let me just quickly go through this. So customers can associate one or more Azure regions with their Cosmos account, and then we perform the global replication across multiple regions. Currently supported APIs are Mongo, Cassandra, SQL, Gremlin, and all of these capabilities are applicable to all of them. The containers themselves, think of them, they're completely schema-agnostic bags of data. So whatever the data you throw at Cosmos, it will happily absorb it and automatically index all of the entities that are stored in it. So what does the system actually look like behind the scene? This is actually the physical view, so that you don't think it's magic. But so you take Earth, planet Earth. These are Azure regions. We're running today across 54 regions worldwide, and the control plane is basically bootstrapped in a data center via this control plane. The control plane itself is fully decentralized, and its state is also replicated inside the Cosmos DB itself. So we can go and basically scale it across the planet. If you zoom in on Azure regions, within the regions you will find the data centers. This is where we have the data center load balancer. Within the data centers, we're running across about 11 to 20 full domains. So if there is a partial outage, or if somebody cuts a cord, or something happens, tornado, hurricane, your replicas and your partitions are distributed across different full domains and availability zones. Then you zoom in on the racks of clusters, you'll find here clusters, both compute and storage. If you zoom in on the individual machine, this is where containers that belong to different tenants are co-residing on exactly the same machines. So this is multi-tenancy at play. With the proper resource isolation, we can densely pack containers that belong to multiple tenants on the same machines and perform and give them resource isolation. So the containers themselves are comprised out of replicas. If you zoom in on the replica, it basically has a co-located database engine, admission control, resource governor, and within the database engine itself, you will find the typical components of a database engine, plus a lot of other interesting stuff that we've added. One is the actual storage engine, the fact that we're storing index, row store, and the column store, optimized for both operational as well as analytical workloads. So the global distribution, this is the experience that we provide to the users. You can come in, click on replicate data globally. We provide you with the world map, and you select where you want your data to be. Then you click a save button, and that's it. So at any point in time, you don't need to pause your application, you don't need to redeploy it. You select the regions where you want you to be, and that's it. You can also specify the priority list of the regions, so that in the unlikely event, if there is a disaster, let's assume there is a regional outage, basically all of your rights will automatically flow over to the secondary region in the priority list that you specify. Okay? So this is what we call turnkey global distribution, by virtue of just turning on where you want your data to be. Behind the scene, this is a little bit of the insights, but you can think of it, the partition is basically the basic Lego block for your data. When you go partition your containers, we shard them using partition keys. Each partition is represented by a quorum of replicas that is represented by where the data is stored in both analytical and transactional data store. We dynamically self-adjust membership and quorums. We have built-in resource governance, leader-follower election, and we enable basically the very flexible split and merge the global replication of these partition sets. This is what the actual global distribution looks like. If we go and look at our telemetry, it's basically a graph that is spreading across, and you can see basically all of the reads and writes are always local to the region where your application tier is. So you should always co-locate your Kubernetes or your Azure functions with the region where that is associated with your Cosmos database. That's how you get the lowest latency. It's multi-mastered, so your reads and writes are always happening locally. So we provide the guaranteed RPO and RTO of 0. The SDKs that we provide are multi-homing aware. So if there is a regional outage, the SDK client is intelligent enough to be able to go navigate to a secondary region and be able to route the request. So as far as your application tier is completely oblivious to potential regional failures or you adding and removing regions. You may only notice the impact in the latency. This is the consistency models. So if you're really fascinated about this subject, if you look at the traditional market of operation with databases, you will typically notice what we call a very extreme binary choice. On the other hand, most traditional databases give you strong consistency with its own trade-offs of higher latency, lower availability, but you get the perfect consistency. Most traditional NoSQL systems give you eventual. Cosmos DB gives you also the 3 intermediate consistency models. We actually have TLA plus specs for all of the consistency models on GitHub, so you guys can go check them out. And it basically gives you a very programmable and very well-defined options in terms of navigating precise trade-offs in terms of performance, latency, consistency, and availability, with failures or network partitions and without. So you can pick the right trade-offs. So resource governance, this is another very important component of the system. Ultimately, so Cosmos DB goes with the provision throughput model, very similar to what DynamoDB offers, but the difference here is our request units abstract basically physical resources like percentage of memory, percentage of CPU, percentage of IOPS, and then they're applicable to all operations that you're running. So you don't need to do separate capacity management for reads or for writes. All of them are applicable to all of the database operations that you're running. Behind the scene, basically, your replicas that belong to the partition get allotted a budget of RUs. And we provide basically resource governance to guarantee that when you ask that you want to perform 10,000 transactions per second, you have these resources fully allocated to you and they're completely ring-fenced from all the other tenants. So you are getting the resources that you got. Okay? This is actually just I took the snapshot from about 2 years ago. Now it's much larger numbers, but you can see just the scale that we're running in. Within a matter of 3 days, we're supporting services running 3 trillion transactions in just 3 days. This is a telemetry view. Zooming in on one of the clusters. This is multi-tenancy in real life. So think of it this way. These are the clusters that are in region central US with the replicas and partitions belonging to different tenants co-located on the same cluster, serving the data in real time. This is zooming in on the individual machine, how we go and partition resources and allocate them to different tenants, and within a single machine, how the resources are properly isolated to serve the requests to the tenants. So, in conclusion, Cosmos is Microsoft's globally distributed database service. It's one of the foundational Azure services. We've battle tested it massively with our internal workloads. Multi-master replication, global distribution, fine-grained resource governance, partition management are the core foundational principle of the service. And then the precisely defined multiple consistency models provide you with a clear trade-offs for your data. The SLAs and the latency and the throughput availability is something that we as the engineers inside Cosmos are super proud of. It took almost 10 years to get to that level, but this is really exciting. We're also hiring, so if you are excited about this mission, looking for cosmonauts, you can go to the site joincosmosdb.com, and I will pass it on now to Mikhail, who will show how to use Cosmos to build event source and serverless applications.
Thank you, Rimma. Yes, so now I want to take this greatest database of all time and then show in just 15 minutes how you can use it to actually build the application in Azure, globally distributed and using all the power of Cosmos DB. And of course, Pulumi. So I'll start simple. Let's say I'm developing a service, a microservice in an e-commerce application. I want to show a product on a web page or something like that. And I start simple. I only have 2 components in my application at the moment. One is Cosmos DB and one is Azure Functions, which is a serverless, event-driven service in Azure. And for starters, I just deployed to one region here in the US. I use Pulumi for this in TypeScript, so that's how my TypeScript program can look like. I start with a resource group, which just has a name. It's like a container for resources in Azure. And then the location of that resource group is going to be defined by the configuration of my stack. So I can configure it to deploy in different regions if I want to. And then I have a resource, a component for Cosmos DB. And the important bit here is how I configure locations. You can see based on the name, geolocations, that it could be an array, but for now I just use one location and deploy it somewhere in the US. And then I need to define an Azure function for my app. And I chose to use a component called HTTP event subscription. And the cool thing about this component is I can define the code of my application right inside my Pulumi program. So I just type a JavaScript function. I do whatever I want there. And Pulumi will take care of packaging it as Azure expects it, deploying it to Azure, and configure my application exactly the way Azure wants it to be. And I just write a JavaScript function with request and response and do whatever I want there. So another cool thing there is like in the body of that function I can just use a variable Cosmos account that I just defined on the previous slide and use it as just any other JavaScript variable. I can get keys from my connection string just out of there without taking much care. And Pulumi will be smart enough to start deploying with Cosmos and getting the keys from that Cosmos account, packaging it, passing it into my callback function, package it as a zip file, putting it somewhere in storage, and then loading the function up to use that zip file. All done for me, I just write the function. So this is my first version application. I run Pulumi up, wait several minutes. I get a resource group, a Cosmos DB account, and then several resources which are required to run the function app. A storage account, a zip file, consumption plan, and function app itself. So now I can run it, my product page works, and I'm sitting here in the US, I'm a happy user. I sit close to the application so I'll get the best possible experience. But my e-commerce site is global, so I have customers in Europe, I have customers in Asia. And if I measure the latency from those locations, it's not going to be that great. Like from San Francisco I might get 100 milliseconds. But from Europe, from Germany or Hong Kong, I get like 400 milliseconds. If I have multiple subsequent requests, it starts to build up really quick and I get basically worse experience for the outside world. That's not what I want, of course. I want my customers to be happy. So let's make the distribution, the application distributed globally. So I started with Cosmos DB, and I will not be clicking the portal to make it distributed. I'll just change my Pulumi program. I make one extra configuration which lists all the locations where I want it to be. And then with TypeScript or JavaScript, I parse that value. I create a JavaScript array with strings. And then the other thing I need to do is to map this array into an array of objects which will be compatible to the Cosmos account resource. That's again just one call to TypeScript map function. So I do that, I run Pulumi up again, but it doesn't help. Of course, because my customer still talks to function app, it doesn't talk to my Cosmos DB account directly. So it still makes a round trip to US, and then the US function app talks to Cosmos DB. That seems to be a trivial mistake, but when your infrastructure is big, when Cosmos DB is managed by one team and application managed by other team, it's quite easy to make this mistake in a real production application. So let's see how we can fix it. Instead, I want to deploy function app into every region, the same regions that I deploy Cosmos DB. And then I want to configure routing so that users from Azure are routed to the closest location, users from Europe are routed to the closest location, and in the US, and so on. So I can take so many regions I want, I just need to copy the infrastructure and make a front-end route and choose the better one. So my plan for the second iteration of my app, I have Cosmos DB at the backend, which takes care of the hard stuff of distributing the data. And then I copy my function app n times, and I put Azure Traffic Manager, which is like DNS-based routing service in Azure, in front of it. And I say, please route it based on the nearest location. In terms of Pulumi, I already changed the Cosmos DB, so I need to change function app now. I just have a loop. I loop through locations, and for every location I create one event subscription. And subscription is going to be exactly the same, except that it's in a different location, and then it connects to a different region for the Cosmos DB. And in the end, I get an endpoint, and I need to use this endpoint to configure the traffic manager. The traffic manager, I define a profile, which is like global thing, which has DNS name and routes and method. And then again, I have a loop which goes through the same location area. And for every location, it creates an endpoint in traffic manager. And then it links this endpoint to the proper function app, just by URL or the ID of the resource. And that's it. When I deploy, the problem is fixed. The latencies are good wherever I am in the world, or just wherever my customers are. That's not the end. I go to my other team and I explain what I did, and they say, yeah, we need exactly this, but we don't use Azure Functions for this. Let's say shopping cart service is using Go, and then they package it as a Docker and put somewhere in Azure container instances. But they want the rest of my application to work the same. They still want to be global. They still want to use Cosmos. Maybe my pricing engine team has like 1 million lines of Java, and the application only runs in one specific version of operating system. So they have to deploy it on virtual machines, and they put it on VM scale sets. They have a load balancer in front, and public IP, all the networking, security configured. That's already hard enough, but now they have to make it global. And it's quite easy to make a mistake there. So how can I help them? Well, I can notice that there is a pattern there. I have a backend configured for Cosmos DB. I have a front end with Traffic Manager. And then I have some compute which does stuff on their own and provides an HTTP point which I should connect to. So I can make an abstraction, and as I would do it with a normal generic purpose programming language, I can create a component for this. So I can create a component which is called global app. And it's a really simple one. I can pass a resource group, a list of locations, and then like a callback function to provision the custom resources per use case. So the callback will do two things. It creates some global resources specific for the use case, and then for every region it would create a copy of infrastructure in that region. So to explain, I'll give an example. For my function app use case, I don't need any global infrastructure. I just create a callback again that creates HTTP event subscription. So instead of going through the loop myself, I delegate this to component, and I just have a function which creates it in one location. For containers, I guess it's not very readable, but I have two blocks here. One creates an Azure Container Resource registry, makes a Docker image, puts this Docker image in the container registry. I can still do everything inside my Pulumi program. And then I have a callback, which again uses the JavaScript closure to use that container registry and Cosmos DB account to create Azure container instances and configure it properly to connect to the right region, and then use the right Docker image. So in the end, it just returns again an HTTP endpoint, and that's all my component has to know. And for my pricing team, they create all the infrastructure which I cut here, but you can see that it's like a dozen of resources just to run it. But still, it's much easier than if they had to do it themselves on a globally distributed way. So, a couple of benefits that I get from this. I can also evolve this component separately from my end users. So, let's say I didn't need a multi-write distribution for my product service, because products, they are not changed by end users. But then my shopping cart team asks me to add this multi-mastering capability. So I just create an extra option, and I can distribute a new version of the application, of component, of the library, and then everybody can benefit from it. But let's say I want to swap Traffic Manager with like another service in Azure Front Door, which is like a CDN. They have edge locations around the world, and then they get your traffic, and then it travels through Azure networks. So it might be faster for my use cases. So I just swap one service with the other inside the component. I make a new version, and then everybody who wants to use it can just update their packages, and they basically don't have to think about this that much. So to wrap it up, yes, perfect timing. So we looked at the power of Cosmos DB to solve the hard problems of distributing data around the world. And we can, but it's still not trivial to create applications which would be globally distributed and would embrace this power to full extent. So we can use infrastructure as code to do this configuration properly, written once and then distributed between multiple teams. And we can also create abstractions which would codify some best practices. Like people, not everyone would have to think of them again and again. We just share it between the teams in the company or even between the community. So if you want to know more, there is a blog post which outlines this a little bit. There is a component on my GitHub which does exactly this. And then if you want to start with Pulumi in Azure, there is a nice case like that. That's the last one. So thank you, I think we are done and good for beers.
Definitely, I don't have much to say. I just want to thank the speakers again. I think it was definitely tough to speak over the noise, but I think they did a fantastic job. I definitely learned a lot, and we recorded it, so it's going to be up online. Anyway, just thanks for coming. This is the first of hopefully many. I mean, we're planning on kicking up, Pulumi user groups around the world. We're already seeing a lot in Europe already, so hopefully we see continue to pick up on that. And if you haven't given it a try, download, join the Slack.